Math 1343, testing means. Testing one population mean critical value approach. On the side here, I've summarized the 5 steps for testing in general using the critical value approach. State the hypotheses, sketch the regions and find the critical value, calculate the test statistic, make a decision, and then answer the question. As we go through this example, I'm going to point out the things that are different between testing one population mean as opposed to last week's testing one population proportion. The flow is the same, but there are 2 key places where we need to make some changes. All right, so let's take a look at this example. A company claims the average salary of its employees is $30,000 a year. Right out the gate, you should be able to sniff out a hypothesis there because somebody is making a claim about a population, in this case, the population of employees. A labor union can test this claim. They surveyed 35 employees and their average salary was $29,000 a year with a standard deviation of $4,000 per year. Remember that the gist of a hypothesis test is that somebody claims something and somebody comes with some evidence to the contrary, and then we determine whether or not the evidence is sufficient to reject the initial claim. Tested alpha equals 5% if the union can conclude the average salary for all employees is less than $30,000 per year. Can we conclude the company's claim is invalid? All right, so we got all the makings of a hypothesis test. Before we jump into these steps, let's go through the problem and extract the information that we're going to use. Excuse me. The first sentence says a company claims the average salary of its employees is $30,000 per year. Since we're talking about the average of the employees, and it doesn't say the word all, but I'm going to sneak it in here to emphasize that they're making a claim about the entire population of employees, then the variable for population average or population mean is mu, and the company is claiming that it's equal to $30,000. So they are claiming mu equals $30,000. But this is a claim about a population, and therefore this is a hypothesis. Which one is it? Well, we'll talk about that when we do step 1. A labor union can test this claim. They surveyed 35 employees. There's our sample size. So right here, we can pull out n equals 35. And their average salary was $29,000 per year. It's an average, but it's an average from a sample of 35 employees. How do we know there's not more than 35 employees? Well, if there were 35 employees, then this would be the exact average and not just the average for a sample. And there'd be no need to contest it. Let's see. So the average of the sample was 29,000, and that's an X bar value. So X bar is equal to 29,000 with a standard deviation of $4,000 per year. This still comes from the sample, so that's the sample standard deviation, whose variable is S. So we can also pull out S equals 4,000. Tested alpha equals 5%, so here's our significance level, explicitly stated as alpha. If the union can conclude that the average salary for all employees is less than $30,000 a year, this is a claim about a population, emphasis on the word all. So they're trying to conclude that the average salary for all is less than 30,000. So there's another hypothesis. You're not always given both hypotheses, the null and the alternative, but in this problem you were. All right, so now that we've extracted all the information that we can from this problem, let's go through the motions of the hypothesis test. Starting with stating the hypotheses. Recall that the notation for the null hypothesis is H0, H subscripted with a 0, and the notation for the alternative hypothesis is an H subscripted with an A, HA if you will. These are not variables, these are simply abbreviations for the phrases null hypothesis and alternative hypothesis. The correct notation has a colon following each of them, then the claims about the hypotheses, which we have both. Claims about the population, which we have both. Mu is equal to 30,000 is what the company is claiming. The labor union is countering with mu is less than 30,000. So which is which? Which is the null and which is the alternative? As I stated in the video about stating hypotheses, there are a couple of ways to view what a null hypothesis is and what an alternative hypothesis is. Some professors in some books say the null hypothesis is the norm. It's what we think is true unless there's evidence to the contrary. But from a technical and from a mechanical perspective, there's a much more objective way of saying who's who. The objective way is the null hypothesis always permits equality, and the alternative never allows it. Because mu equals 30,000 not only permits equality, but it demands it, that's our null hypothesis. Mu is equal to 30,000. The other hypothesis, mu is less than 30,000, prohibits equality, so that's our alternative hypothesis. Before we move to step 2, I do want to remind you that the alternative hypothesis is the one that determines if this will be a left tail, a right tail, or a two-tail test. Since the alternative hypothesis contains less than, that means that we are going to conduct a left tail test. If I can write here. All right, so there's step 1. Step 2 is to sketch the regions and find the critical value. To sketch the regions, start with the bell curve, and then shade in the left, right, or two tails, depending upon the alternative hypothesis. Since this alternative hypothesis was less than, this is a left tail test, and we will shade the left tail. And recall that the significance level is the probability of, is the tolerable probability of allowing a type 1 error, of rejecting a true null hypothesis. But in the flow of a hypothesis test, the significance level just represents the area of the tail or tails. Since there's only one tail, this whole tail's area is 5%, or 0.05. If it were a two-tail test, then we would have cut that 5% in half and put 2.5% in each tail. As far as the regions, the region containing the center is always the non-rejection region. The tail or tails is the rejection region. And the only thing left now is to calculate the critical value, which is the score that separates the regions from each other. And here's the first main difference in what we did last time with testing proportions versus now testing means. When we test proportions, we use the z distribution. But when we're testing means, we use the t distribution. So in the second step, I'm going to make a note that you use the t distribution. But you may recall that the t distribution requires degrees of freedom. The formula for degrees of freedom is the same as it was when we were doing a confidence interval for means. The degrees of freedom is the sample size minus 1. So we'll have to get out the t-chart, and I've got mine pulled up here, and I'm not going to move the camera to show it to you. But our degrees of freedom in this one is going to be the sample size, which was 35, minus 1, so our degrees of freedom is 34. So without me showing you the t-chart, because you should have access to one by now, you would go to the 0.05 column, which is the second column, and then you would go to the 34th row, the degrees of freedom 34. So row 34, second column, and the t-score is 1.6909. T equals 1.6909. Except it's not. You know why it's not? This is a left tail test. The t-chart talks right tails. Numbers on the left are negative. This is the symmetry of the normal distributions. So there's change number 1. When you're looking up the critical value that separates the regions, you use the t-chart and not the z-chart. So I hope you're fluent with it by now. All right, there's step 2. Step 3 is to calculate the test statistic. And this is the other change in testing, means versus proportions. You'll have to forgive me, I keep pushing my glasses up. I got new glasses yesterday, I'm still getting used to them. To calculate the test statistic simply means to take what your sample gave you and turn it into something comparable to the critical value. So in this context, that means we need to take the sample information and turn it into a t-score. Here are the formulas. First, we have to calculate the standard error, which will be the sample standard deviation S divided by the square root of the sample size. That should look familiar because it was the same standard error for when we were calculating the confidence interval for one population mean. And then our test statistic T is going to be a fraction where we take our sample value, our x bar, and subtract from that the hypothesized value of the mean from the null hypothesis. Mu subscripted with a 0 means this guy. In fact, in some books, when they write the hypotheses, they'll subscript these variables with zeros. I don't think that's essential. The fact that it's after this says it's a null hypothesis. And then we divide it by the standard error. So calculate the standard error, and let me box these because the formulas are kind of running into each other. There's the formula for the standard error, and there's the formula for the test statistic. All right, so let's do that. Our standard error will be the sample standard deviation, which was 4,000, divided by the square root of the sample size, and the sample size was 35. I can't speak for your professor if you're watching this and you're not my student, but my protocol when it comes to decimals is if it doesn't stop at 4 decimal places, round it to 4 decimal places. And if you're wondering why I choose 4, because more decimal places doesn't get us anything better, but fewer decimal places can sometimes lead to different results. You lose too much accuracy. So I've just found that 4 is a nice in-between. Let me do this again because I don't remember that being the standard error when I worked this before, but it's got the same thing again. To 4 decimal places, 676.1234. But that's not our test statistic, that's simply the denominator of the formula for the test statistic. Our test statistic will be what we got from our sample, 29,000, minus what we're claiming in the null hypothesis, which is 30,000, divided by the standard error that we just calculated, 676.1234. Make sure that's a decimal, not a comma. And this will again come out to a nasty number of decimals, so we'll just round it up to 4. And to 4 decimal places, I get negative 1.4790. Let's put a box around the standard error and the test statistics so that they kind of stand out. There we go. All right, all the calculations are done. All that remains now is to make a decision and answer the question. Remember, your decision is one of 2 things. You pass judgment on the null hypothesis, reject it or do not reject it. That decision is based on where your test statistic lands relative to your critical value, specifically which side of it lands on, meaning which region. Compared to negative 1.6909, remember zero's in the middle here, the test statistic, negative 1.4790, is just a little bit to the right of it, negative 1.4790. I'm not worried about specifically where it lands, just relatively that it lands to the right. And it lands in the non-rejection region, which means our decision is do not reject the null hypothesis. And then you can just write H0 for the null hypothesis. I realize that if you read this as a word, that sentence means something completely different, but I'm never going to mention that again. All right, so we don't reject the null hypothesis, which means now we can answer the question. Remember, when you answer the question, you have to ask yourself which hypothesis are they asking that you can claim. Can we conclude the company's claim is invalid? Well, this is the company's claim. If it's invalid, we would have to conclude this one. So really what they're asking is, can we conclude the alternative hypothesis? Well, when you pass judgment on your null hypothesis, you're essentially saying somebody is getting rejected and somebody is not. It's not technically what happens, but for interpretation purposes, it satisfies. When we say do not reject the null hypothesis, we're saying, all right, we're not going to reject you, so we're going to keep you. But we have to keep only one and get rid of the other, which means we have to get rid of the alternative hypothesis. So can we conclude the alternative hypothesis? We cannot. So to answer the question, no, we cannot conclude. We cannot conclude the company's claim is invalid. Does that mean the company's right? Not necessarily. What this means is our evidence is not strong enough to reject what the company says. The company's claim might be wrong. This might be false, and we failed to reject it. We could have made a type 2 error. But at this level of statistics, we don't worry about that. Well, you should always think about it, but don't lose any sleep over it. All right, so just to review real quick, because I know this video has gone a little bit longer than I like. What are we at now? 15 minutes? When you're testing one population mean, it's the same flow with two major changes. Number one, when you're finding the critical value, you use the t-distribution with the degrees of freedom n equals n minus 1. And number two, when you calculate the test statistic, it's a different pair of formulas for both the standard error and for the test statistic.